Okay, so let us now push on to question 57. So, a woman on a bridge 75 meters high sees a raft floating at a constant speed on the river below. So, trying to hit the raft, she drops a stone from rest when the raft has 7 meters more to travel before passing under the bridge. So the stone hits the water 4 meters in front of the raft. Okay, so we've got a sort of before and after. So we want to find the speed of the raft. Now, something that's very important here is that we are dealing with two axes. So we've got a raft that's moving along this way, but we also have a sort of a bridge sort of thing that does not doesn't look like a bridge, but anyway, you guys know what I mean. So we've got someone over here who's dropping a stone. So we've got both an x-axis and a y-axis that we're going to be dealing with here. So biggest thing here is, okay, we sit back and we think and we go, okay, what do these two have in common? Is it the distance? Well, no, not really. Okay, they're completely different. Velocities? They're completely different. The one thing that they have in common is time, because the girl dropped the stone from rest and it hit the water. And during that time, when the stone fell from her hand to the water, we know the before and after of how far the raft traveled. So time is the consistent thing here. So that's what we're going to go with. So the first thing we need to do is we need to go, okay, how fast was that rock traveling? So how long did it take for the rock to leave her hand and hit the ground? So what we do is we know that for the stone, it traveled 75 meters. Its acceleration, because again, it was falling towards the ground, she let go of it. So what made it accelerate? And that is gravity. So we know that the acceleration is going to be 9.8 meters per second squared. And the initial velocity is going to be 0 meters per second because it started at rest. So what we do is now we can calculate the time. So we can go x equals VOT plus 1/2 AT squared. So we know that x is going to be 75 meters. So we've got 75 meters is equal to VOT. So that's going to be 0 because it's starting from rest times time. So that can be eliminated because it's just going to be multiplied by 0. So we have 1/2 of the acceleration. So we have 1/2. The acceleration is 9.8 meters per second squared times time squared. So now is when we can do a bit of sneaky rearranging. So 1/2, we can move this 2 over. So the 2 moves over up here. So it's going to be 2 times 75 is equal to 9.8 meters per second squared times time. Then we move the 9.8 over because this is a times, so that moves over here. So we're going to have 150 divided by 9.8 is equal to t squared. So that means that t squared is going to equal to 15.79. So to rearrange and solve this, remembering the opposite to squared, or the exponent, is the square root. So t will equal to the square root of 15.79, which is going to give us 3.97 seconds. And that is how long it took for the stone to hit the ground. Now, this is where we can look at the speed of the raft. So we know how how long it took for it to hit the ground. So in the time that it took between the stone falling from here to here, this raft moved from 7 meters to 4 meters. Okay? So what we can do is we can simply go, because the question's asking for the speed. It's not asking for the velocity, it's asking for the speed. So we can go the speed of the raft is equal to the distance. So in the time it took for that stone to fall, it traveled 3 meters over how long it took, which was 3.97 seconds. Which means the speed of the raft is going to equal to 0.756 meters per second. Okay, so let us now move on to question 42. So this one is a doozy, okay? This one's very difficult. So this is one of our challenge questions here. So I highly emphasize looking at the lecture questions first, then the earlier questions in the textbook before moving on to this one. So we have a train that is a length of 92 meters, and it starts from rest with a constant acceleration at time t0. So we know it's starting from rest at 0 seconds, and it's going to be constantly accelerating. Now, at this instant, so the train is technically not moving, it's at rest, time is equal to 0. Okay, the car just reached the end of the train. So we've got our train here. God, that's an awful train. Okay, so this is our starting point here. So I'm going to divide this into, so I've got, so 1 is when t is equal to 0. And that means that our car is going to be here. Now the car is moving with a constant velocity. Okay, so we don't know how fast it's going, but it's constant. Okay. Now at time t is equal to 14, the car reaches the front of the train. Okay, so part 2 is when time is equal to 14 seconds. So when time equals 14 seconds, the car reaches the front of the train. However, ultimately, the train pulls ahead of the car, and at time equals 28 seconds, the car is at the rear of the train again. Okay, so when we've got 3, so that means that we're back to where we were. So okay, so we've got 3 different scenarios going on here. So we need to find the magnitude, so how fast the car is going, and the train's acceleration. Now the big thing here is that the acceleration and the velocity are constant. So that means throughout these 3 different time intervals, the velocity and the acceleration don't change. So it means that we can interchange these 3 scenarios here to get our final answer, which is good. That's very good for us. So the big thing here is, so we don't have enough information here. So I'm going to move on and look at part 2. So when we have time is equal to 14 seconds, or number 2, so I'm going to use the formula x equals VOT plus 1/2 AT squared, because at this point is when the car and the train are neck and neck. Okay, so that means we can use this as a bit of a reference point to get some info. So the big thing here is I'm going to try and calculate the velocity of the car. So we can go, because we know too that at this point, at 14 seconds, both the train and the car are moving forward, but it's here that the displacement for both of them will be the same. But, and there's a big but here, yes, they've traveled the same distance, but we need to take into account the length of the train. So I'm going to add that into our formula here. So we're going to substitute this in. So we've got x equals VOT plus 1/2 AT squared. So we've got the displacement of the train is going to be VOT plus 1/2 AT squared, but we have to take into account the overall length of the train as well, because you can see here that the train has got a 92-meter advantage. It's 92 meters ahead. So the car technically has traveled the same distance that the train has, in addition to that 92 meters that the train, that's the overall size of the train. So we need to add 92 meters onto here. So this part here is going to tell us the total displacement for the train. Now we look at the displacement for the car. So we go x equals VOT. So the velocity was constant. So the car's velocity, so we multiply it by time. So time is 14 seconds. So we have VO times T, which is 14 seconds, plus 1/2 times the acceleration. Okay, it's moving at a constant velocity. So if that velocity is not changing, it means that our acceleration is going to be 0. Okay, and our time, t, is 14 seconds squared. So the initial velocity for the train, we know that it started off here at 0, okay, because it started from rest, then it's accelerated to this point. So this is like our start, this is our finish. So we know it started off at 0 meters per second times time, which is 14. So 0 times 14 is going to equal to 0. So that is going to be cancelled. Plus 1/2 AT squared. Okay, so we know that our train has a constant acceleration. Okay, it says that up here. So we know we have 1/2 acceleration times t squared. Okay, so I've just simplified this a little bit for us. So again, we go 1/2 a times 14 squared plus 92. So we take 14 squared plus 92 and then divide that number by 2. So that should give us 98a plus 92 meters. Now we can't add these two values together, what we've got here, because this one is not the same unit. So be aware of your units because you can't add different units together. So it's equal to 14 v car. Because what I've written there is the exact same. It's 14 times v car. So this is going to be our equation A. Because you can see we can't simplify that down any further because we have two unknowns, like with our Knights charging example. So I'm going to put a little square around that, and we're going to come back and visit that one in a moment. Now, let us look at when time equals 28 seconds. So when our time is equal to 28 seconds, we want to compare the change in the distance, okay, in our displacement here, because we can see that the difference between 14 seconds and 28 seconds is that the car has moved from the very front right to the back. So this is where we can see the difference in the train and the car. We can look at how much of a difference there is in terms of how quickly they're covering that distance, and that's when we can look at the acceleration and the velocity for both the car and the train. So how we do that is we look at our displacement again. So we know that the displacement for the train is going to equal the displacement for the car. So because we know that our displacements are going to be the same, so they're both going to be traveling the same amount of distance, we can use the same formula that we used over here, but we're going to compare it at 28 seconds. So for the train, we have, so x equals VOT, so the initial velocity, the train started at rest. So it's going to be 0 times t plus 1/2 times the acceleration, which we don't know, times t squared. So our time is going to be 28 squared. And that's going to equal to So x equals to VOT, so the initial velocity for the car, which we're going to denote as V car, because we don't know what it is, times the time, which is 28 seconds, plus 1/2 AT squared, so the velocity is constant, so the acceleration will be 0, so the 1/2 AT squared gets completely cancelled for the car. So what this means is, if we simplify this, it means we're going to have 392A is equal to 28 times V car. Okay, and that's going to be our equation B. Now, what we can do is, because if we look at 3 and we look at 1, we can see that their situation is almost identical. So instead of both of them being at the very beginning when time is equal to 0, we're looking at the very end when time is equal to 28. So what we can do is, in order to calculate equation 1 over here, what we can do is we can take our equation B here and divide it by the total number of time. Because what that means is, by dividing it by time, we will see what was going on at the very beginning. So we take 392A divided by 28 seconds is equal to 28 V car divided by 28, and that will give us 14A is equal to V car. And that is our equation for number 1. So we'll denote that as C. Now what we've done here is we have been able to, by using a lot of math rearranging, is determine that the acceleration of the train is 14 times greater than the velocity of the car. So what we can do here is we know that 14A is equal to the V car. Okay, so 14 times greater in terms of acceleration when compared to the velocity. So what we do is we compare this to our very first equation over here. So we have 98A plus 92 meters is going to equal to, instead of putting 14 V car, so 14 times the velocity of the car, we know that acceleration is 14 times greater. So we can convert this, instead of saying 14 V car, we can go 14 multiplied by 14. Because that will give us, so if we type 14 times 14, you're going to get 196A. Okay, so we've sort of substituted that value in. So now, instead of having 2 unknowns, we have 1. So we can rearrange this, so we can go 92 meters is equal to 196A minus 98A. So we go 196 minus 98, which is going to give us 92 meters is equal to 98A. So we rearrange this, so this is a multiply, so we move it around so it turns into a divide. So we will have 92 meters divided by 98 is equal to A, which means that our acceleration is going to equal to 0.94 meters per second squared. So that is going to give us our total acceleration. So this is how much the train is accelerating by. So now we can use this to find out the overall velocity of the car. So we know that 14 times 0.94 meters per second squared is going to equal to the velocity of the car. So 0.94 multiplied by 14, that's going to give us 13 meters per second. And that is the total velocity of the car, and that is the total acceleration of the train. Okay, so let us now push on to question 63. So while standing on a bridge 15 meters above the ground, you drop a stone from rest. When the stone has fallen 3.2 meters, you throw a second stone straight down. Okay, so I've got a system that is involving two different objects that are moving. So what initial velocity must you give the second stone if they are both to reach the ground at the same instant? So take the downward direction to be the negative direction. So, big thing that's popping out at me here is that we have, I'm not going to try and draw a bridge, sorry. So we've got our main distance here, so we've got someone standing up there and they're dropping a stone. So they're dropping a stone 15 meters. So down here will be 15 above the ground. Now as the first rock, so we'll call that 1, drops down to 3.2 meters. My scale's a bit off, okay, don't judge. A second stone is thrown. So it means it's not starting from rest, it's actually thrown downwards. Okay, and now what we want to know is how much what velocity must we give this second stone for both of these to hit the ground at the same time? So time there is, or the same instant. So that is a really key point here. So the first thing we need to do is we need to look at this and go, well, okay, how long did it take for that first stone to hit the water? So how we do that is we go, so we'll look at stone number 1. So x equals VOT plus 1/2 AT squared. So x, so it traveled 15 meters, is equal to VOT. So the initial velocity, because it was from rest, so that's going to be 0 times time plus 1/2 AT squared. Now the acceleration is due to gravity, so that's going to be 9.8 times t squared. So what we're going to do here is we're going to go 0 times t is obviously 0, so that's going to be cancelled. 1/2 of 9.8 times t. So we're going to have 15 meters is equal to 4.97 t squared. So what we can see here is we've got a multiply here, so we're going to move this over. So we've got 15 divided by 4.97. So t squared is going to equal to 3.06. So looking here, we can see we've got t squared. So we don't want squared, we want just normal time. So remembering that the opposite to squared is the square root. So how we get around this is we go t is equal to the square root of 3.06, which means that time is equal to 1.75 seconds. Okay, so this is useful. We now know how long it's going to take this first stone to drop all the way down to the bottom here. But what do we know about this second stone? Okay, this is where things get a little bit tricky. So another thing we have to do here is that because we don't know the initial velocity, we're sort of in a bit of a jam here. So we need to look at, okay, well, how long, what is the time difference between this part here? So we know how long it took for our stone number 1 to travel from the very top here all the way to the bottom. But how long did it take for the first stone to travel 3.2 meters? So that's what we need to look at here. So we use our formula x equals VOT plus 1/2 AT squared. So our displacement is 3.2 meters, because again, we want to find this part here. So we go 3.2 is equal to VOT, so we're going to go 0 times time, plus 1/2 AT squared. So we're going to 1/2 9.8 t squared. So what we do is that's going to be 0. 1/2 of 9.8, as we calculated over here, is 4.97. So we're going to have 3.2 is equal to 4.97 t squared. So this is a multiply. We're going to move this over to form a divide. So we're going to have 3.2 divided by 4.97 is equal to t squared. So we solve that, and that's going to give us t squared is equal to 0.653. So because we've got our squared here, we take the square root. So t will equal to the square root of 0.653. And that will give us a total time of 0.8085 seconds. So what we just did there was, we found out, okay, our first stone, from it to travel to the very top, all the way down to the very bottom, will take 1.75 seconds, okay? We also found out that it took the first stone 0.8085 or 0.81 seconds to travel from the very top here to that 3.2 meters. So that means that between the first stone being dropped and the second stone being thrown, there was a 0.81 second delay. So that means is we know that the time for the stone number 2, so this stone over here, must be the difference between these two, because we know, because this is what the question is asking for, when they both reach the ground at the same instant. So both stones hit the water at the same time. Because of that, we know that A, we've got 1.75 seconds for the first stone. We also know that there was a 0.81 second delay. So what we can do is, so for the time for stone 2 is going to equal to 1.75 minus 0.8085, which means the total time for stone number 2 is going to be 0.942 seconds. Okay, so now we're getting somewhere, because now we know how long it took that second stone to hit the water. Okay, so this is really, really important. So what we can do now, because we know how long it took that stone to get there, and we know the total distance that it's going to travel, we can now calculate the initial velocity. So again, we go, okay, but we change things around a little bit. So we have our displacement. So the total distance that stone number 2 traveled was 15 meters, is equal to VOT. So we don't know VO, but we do know time. So I'll just write it now on this new slide, just so we have a little bit more room. So we know that the initial velocity, well, that's what we're trying to find out, but we have been given our time. So it's going to be VO multiplied by 0.942 seconds plus 1/2 acceleration. Okay, so the acceleration is 9.8 and t squared. So our time is going to be 0.942 seconds squared. So now is when we start to rearrange and we start to solve. So we're going to have 15 meters is equal to 0.942 VO plus, so we have 1/2 of 9.8, so that's going to give us 4.97 multiplied by 0.942 squared. So 4.97 multiplied by 0.942 squared will give us 4.348. Okay, so now we simplify it even further. So we have our addition here. So I'm going to move this number over to this side. So we're going to have 15 minus 4.348 is going to equal to 0.942 VO. Then we've got a multiplication. So that's going to turn into a divide. So 15 minus 4.348 divided by 0.942 will equal to VO. And that's going to give us an initial velocity of 11.3 meters per second. And that is how fast that person had to throw that stone initially for it to hit the water at the same time as stone number 1. Okay, so let us now look at question 85. So a police car is traveling at a velocity of 18 meters per second, due north. When a car zooms by at a constant velocity of 42 meters per second, due north. So we've got a police car who's traveling this way at his velocity there, and we've got someone just smashing past him. So after a reaction time of 0.8 seconds, the policeman begins to pursue the speeder. So all of a sudden the cop here is going, oh, hang on, and he goes to give chase. So the policeman will start to accelerate at 5 meters per second squared. Now, including the reaction time, how long does it take for the police car to catch up with the speeder? So, okay, biggest thing that we need to do here is we can see that the question is asking how long does it take for the police car to catch up? So it means at what time will both the displacement for the police car and the speeder be the same? So when they reach the same point here. Now, for us to do this, we need to look and see how far each of those cars had traveled before the policeman gave chase. Okay, because although the speeder is going at a constant velocity, the cop car isn't. The cop started at 1 speed, the person overtook him, and then he's given chase. So we need to look here. So we need to take into account, so I've got the reaction time. So we have the policeman. So the policeman is going at 18 meters per second multiplied by 0.8 seconds. So that means he traveled 14.4 meters. Then we look at the speeder. So he was going at 42 meters per second for 0.8 seconds equals 33.6 meters. So what this is telling us is that the cop was going at this constant velocity for 0.8 seconds until he put the pedal to the metal and started to give chase. So that means that during that time when the cop was reacting, he traveled 14.4 meters, but the speeder traveled 33.6 meters. Okay, so this is going to be our initial sort of distance covered. So because we now know the initial distance that they covered from the starting point, we can now calculate the total distance traveled. So there's a couple of things that we can do here. The first thing is we need to acknowledge that with displacement, okay, displacement is distance final minus distance initial. Okay, so we need to keep that in mind, because what we can do is we can use, now another way that this can be written is x, so displacement final minus displacement initial is going to equal to, but because this question we need to find the final distance, so how far did they travel? Because the reason is, for the speeder and the policeman, they're going to be the same, because it's how long did it take for them to get to the same, like neck and neck. So we can move our initial over, so this is a minus, so it's going to turn into a plus. So this is how the final equation is going to look. Now the big thing is, again, is that the final displacement for both the policeman and the speeder are going to be the same. So what we can do is, we can substitute this formula in to both the police and the speeder. So before we start sort of getting too crazy and fusing equations together, let's have a look first. So we've got the speeder. So the displacement final, which we don't know, so it's going to be xf, is equal to the initial distance. So the initial distance we calculate it over here, so it's going to be 33.6 meters plus VOT. So we've got the initial velocity, which was 42, times time, because we don't know. Because remember, they're going to continue until the cop reaches the speeder. After that, it's like ding, job done, stop, end of game. So we've got time plus 1/2. Now, the acceleration for this car is 0. Why? Because he's going at a constant velocity. Okay? If he's going at a constant velocity, he's not accelerating nor deaccelerating. So A is going to be 0 times t squared. Now, for the cop, we have displacement final is equal to the initial displacement for the cop, which is going to be 14.4 meters, plus VOT. So the cop was initially going at 18 meters per second, times time, plus 1/2. So the acceleration for the cop was 5 meters per second, times t squared. Because again, we're trying to find time. Okay, so we've got our two formulas here. Now we can fuse them together. So we rewrite this, combining both of them. Okay, so now that we've got this, we're now going to start to simplify. So we're going to have 33.6 plus 42t is going to equal to 14.4 plus 18t plus 1/2 of 5, so half of 5 is 2.5 t squared. Now, very, very interesting, because what I can see here is we have a known value, we have our unknown, and we've got our unknown squared. So that points me to use a quadratic formula. So when using a quadratic formula, we want to rearrange everything so that it's equal to 0. So we want to move everything to the right. So we're going to have, so if we move these over, we're going to have 0 is equal to, now I'm just going to shuffle these around a little bit so that we've got our t squared, our t, and our known value, because that's going to be A, B, and C. So, using the quadratic formula, our time is going to equal to, you do not need to memorize the quadratic formula, okay? It is not expected of you in this course. This is a challenge question. So what we do is we substitute our A, B, and C into these values here. So we're going to have t is equal to negative, because don't forget it is a negative here, plus minus the square root of b squared, so negative 24t squared, plus 4 times 2.5 t squared, plus 19.2 meters, divided by 2a, so 2 times 2.5 t squared. Okay, so now we need to start on doing some serious simplification. So the first thing I'm going to do, so 24 squared. So we're going to have, so negative and a negative equals a positive, so we're going to have 24t plus minus the square root of, so negative 24 squared is going to give us negative 576 plus 4 times 2.5t squared, that's going to give us 10t squared, negative 19.2 divided by 2 times 2.5t squared, so that's going to be 5t squared. Now, t squared here and the t squared here, they can cancel. So that's going to give us 24t plus minus square root of negative 576 plus 10, 19.2. So that's going to give us 24t plus minus square root of negative 576 plus negative 192 divided by 5. So if we go 576 plus negative 172, and we take the square root of that, that's going to give us, so if you punch that in your calculator, you're going to get 22.7. So we have our 24 out here. So t equals 24. Now it says here plus minus, okay? We're trying to find time, so time cannot be a negative value, so we're going to take the plus. So it's going to be 24 plus, now the square root of negative 576 plus negative 192 is going to give us 22.7. We're going to divide that by 5, which means that our total time is equal to 10.34 seconds. But before we celebrate too hard, yes, that is how long it took for the cop to catch up to the speeder. But we need to remember that it took that police guy 0.8 seconds to react. So we need to take that into account. So we need to go 10.34 plus 0.8 seconds, which means the total time is 11.14 seconds. Alrighty guys, thank you very much for joining me on this video. I hope you weren't too overwhelmed about the challenge questions. If you do have any questions, queries, ideas, suggestions, anything like that, please feel free to hit me up on my email at b.grant@griffith.edu.au. Again, don't forget to do the surveys for me, please. They really help me out a lot, and it gives you, again, an opportunity to go into the draw to win some awesome prizes. So my name is Brock Grant. Thank you very much for joining me today, and I'll see you next time.